your dedication for our profession, and even under this very difficult time. So I truly respect you, and I hope that the war will end as soon as possible. Okay.
Thank you.
Thank you. So this is my the model of my talk, and I just want to remind you the previous talk was also in this similar model. That was the day before that the war broke out. So this time, the difference is before that we were talking about that's the system under that under that the Skorohod regime. Now this talk, the difference is that is under the Stratonovich regime. So here, that's the randomness come from that's the Gaussian field W dot, and in this talk, the W dot only depends on the time the space. So that's why we call that the time independence, and the space dimension also is 1, 2, 3, and later on I will tell you why we only limited our attention to those 3 dimensions. Okay. Mathematical definition of the system is by this stochastical integral equation, and where that's the stochastic integral is given in the sense of the Stratonovich, which means that you first start with this integral, the ordinary deterministic integral, and we smooth the noise. And then if this integral converges in a proper way, for example, convergence in L2, then that will be the definition of this stochastic integral. And you can say in this way of the discussing, our system is very much close to that's the deterministic calculus. Okay. Where that's G is a fundamental solution in that. Okay, so defined by this deterministic partial differential equation, and then later on I'm going to give a little more details about the G. Actually, here that's some properties of the G play an important role for our way of solve the problem. Okay. So again, since we have a linear system defined, let me just go back to this, defined by this integral equation. So if you iterate this integral equation and infinite times, you are going to get this kind of expansion, and with this recurrence relations, if you keep the repeat this recurring relation, and you are going to say that essentially that general term will take the form like this. So that is so in this way we get that's a kind of expansion. And I wanted to make a remark. Essentially, this expansion is what's called by Dalang and Mueller and Tribe in their earlier papers as they call this as a Feynman-Katz formula. Now the question is, of course, first of all, you can imagine that the issue of solvability, which means existence and uniqueness, is largely depends on how well this infinite series converges. So in the paper, I just will collaborate with Yaozhong, who the first part is solvability. So we basically prove that under that the Dalang's condition gave here, that this infinite series converges properly and is a solution of the equation we are talking about.
Excuse me, what is mu?
Oh,
In
I'm sorry,
Poland
I did
condition?
not say that. Okay, so maybe let's see next page. Yes, here is the mu.
Yeah.
Yeah. So the mu is spectral measure of that covariance, because covariance, as a is a non-negative determinant, definite. So that's the sure that's the spectral measures, and so basically the condition we give here. Oh, something happened. I don't know what's happening. I cannot move. That's the. I cannot move this things back. Okay. Anybody knows what's the problem here? Okay, now. Okay, so in this talk, we were. Okay, so yes, okay, now it's fine. So I just want to say that this type of conditions basically is to control the tail of the mu. So by the Fourier analysis, that basically says under this condition that the singularity of the gamma and zero have some kind of control. That's basically is about this condition is. So here is a prior earlier result, and under the stronger condition. And we believe that the Dalens condition is the base conditions for that solvability. Okay, so, but this is not the main topic of our talk. The main topic of our talk is the intermittency of the system. That means that we care about the asymptotics of the solution or moments of the solution, either when t goes to infinity or when the p goes to infinity. That's something that the physicists like to, know. So then we are going to put this condition will be put in our talk. That is the homogeneity of the covariance function. But under this condition, the Dalens condition actually is equivalent to that the alpha is less than 2. So that's will be our new condition, and for for main result. Okay, here is our main result. The first result is that when the t goes to infinity, p is fixed. The p is fixed integers. And second condition is that when the t is fixed and the p goes to infinity. And here, if you compare those two conditions, and you say that's a kind of universality, means those two results looks more or less the same if you just interchange. That's the limit between t and p, nothing different happening. Indeed, so I call that universality, and that's basically you can imagine that's essentially come from the homogeneity assumption we give. So you can that allows you to scale your variable from this space to the time, and from t to the p. Okay. So that's our main result. That's the only result, the main results in this talk. So we can have some simple corollary. That is, if you take a special and important case where your Gaussian noise is white, one-dimensional white, that's the case included under our assumption. The reason we can have this kind of clear results because in this case, that's a variation m can be evaluated explosive. Okay.
But what is the a condition of gamma to be homogeneous now.
Okay, so you say that in this case, of course, this is a homogeneous gamma. This case, gamma is homogeneous. And with
Why,
alpha,
how we extract this C from the sine of delta function?
So is alpha 0?
sorry?
What is alpha? This index.
Okay, alpha is one. Yeah.
Alpha is 1. Mm.
Yes. So
So
remember, the
this is
condition is alpha equal to is less than 2.
Now we understand the extraction of C from the sine of delta function, like we do some change of variables in the integral. Yeah.
Right. Right.
Okay.
Okay. So can I continue now?
Yeah.
Okay. So that's just a simple corollary because M can be evaluated explicitly. Okay. Now let's talk about. Okay. So this is a. I want to remind you that my previous talk, we have a similar results in your seminar, where that's the regime is Skorohod, and so the right hand side constant is slightly different, but mostly remain the same. But the condition is different. Here, you are now the alpha is less than 3, but in the Stratonovich case, alpha is less than 2. The reason for that, because in the Skorohod case, we have some kind of renormalization. That is, the correct term. That's reduce the degree of the singularity. So that's my explanation for that. Okay. Now let's talk about the proof. This part of the discuss is a standard. So here is. So we start with this series expansion. So the question we ask, what can we do, and how can we take information we want and do something from this expansion? That's always my goal to study. And we did this for the Skorohod regime, where this expansion is Ito, Wiener expansion. But now let's say that's the Stratonovich expansion. And here, this is what we can do. Okay, here it is. So you take that, raise that to the p square. And so that's just a pure algebra will give you this form of a summation. Then you take expectation to here. Keep in mind, under our assumption, we have a scaling properties, means we can scale this t out of that this product. So we get something like this. So the t after scale out, you raise the power like this, and now the time inside this moment is 1. Okay. So then the question is, if what we this will tell us if we take the limit. Let's say the t goes to infinity. So the key thing to solve that problem is to establish this kind of high moment asymptotics, to say that when n is go to infinity, and if you get this, actually that's the main, a part of the proof that we are going to get this. Let's assume if we get this, then remember this our goal to evaluate the limit like this. This is the moment of the solution. So if you know the behavior of this thing, so you can replace this part by that by our the high moment asymptotics by this quantity, and so you will get the evaluation of this limit, where we use elementary fact of this. Well, you see this is the fact that when gamma is 1, of course, that's just a simple Tanner expansion of exponential function. Gamma is different than 1, then you have to do some trick. For example, I think the essential tool to establish this is Stirling formula. Okay. So let me just repeat. This is something we need to do. If we finish this part, we finish the proof. So now I want to show that what's the main idea to do this. Where is that? Some page is missing, I believe. I don't know what's happening. Okay. Okay, so I apologize. I don't know what's happening. There's a piece, the page is missing, but I try to say the main idea is show that this function, that's the Green's function, is associated with the Green's function given here, where the P is that's the same Brownian semi group. Okay. I don't know what's happening here, so that is. Okay, so I hope I can, make up what's the missing page. So let's say we are going to use. So the key thing is that's for that series expansion, we try to represent the general moment by Brownian motion. And so in that the paper by Dalang and Carl Mueller and Tribe, they basically says that there's no hope to represent the moments by any Markov process. I'm not challenging their claim. I just want to say yes, they are hopeless. But if you consider replace that deterministic time by exponential time, everything changes. You can represent that by the Brownian motion. So that's what I claimed. I hope we don't miss too many pages.
And what is PTX?
Sorry?
What is PTX Gaussian density?
PTX is a Brownian semigroup.
Mm-hmm.
So this G is a fundamental solution of that wave equation. And I try to connect them. So like I said, I want to represent my moments, in that expansion by Brownian motion. So that's why I want to change that G to P. So I try to say how that will work in our favor. Okay, here it is. So I'm going to take exponential time to the moment. Remember, this is a general term in our moments. Okay, so in order to make that connection to the Brownian motion, so I take exponential time. And this Sn is given like this. Now, what I'm going to do is I'm going to take this exponential time into, to here. And you say that exponential time will change that the convolution given here by, to the product. So that is what we gave. Here I have to say that I just do this computation symbolically, because basically you are not allowed to write that the W dot as an ordinary function. But for the simplicity, I just did this And you can, if you don't like this, you can think that the W dot is replaced by its smallest version. Okay, then we can do that. Okay, so you get this. And remember, I said that this part, in this part, you can replace that G by P. Okay, here it is. So once you replace that, then you just take it back and to go to back to original state, and where the only thing changes is essentially you change that G and replace that by P. Okay, if you did that, then keep in mind that this thing appeared in the previous page is a joint density of this Brownian. So this random vector, you know, formed by Brownian motion. Okay. Therefore, this thing is equal to this. So if you just bring that back to our computation, so this is what you get. Now this final step is just the algebra computation. And actually, this is a missing page. This is the missing page. Missing page lists this as a theorem. And so this theorem basically says, yes, we cannot represent that's the chaos expansion in terms of Brownian motion. However, if I change the time, if I can instead consider the exponential time, then this thing will associate with the Brownian motion. And that's the key, step for our the key ideas in our proof. Okay, so this is so the previous discussing is just a proof of this identity. Okay.
Excuse me, can we try to find maybe some kind of stochastic partial differential equation related to this connection to the Brownian motion? Maybe some here term can be involved in the initial equation.
Here you notice, Andrew, I take that's the simplest initial condition because I don't want to make things complicated.
Mm-hmm.
I don't know that's maybe that's if you make some more general conditions, you follow our approach. You first have to reduce that by some kind of comparison, reduce that to our simple initial conditions and use this strategy.
Mm-hmm.
But I have not yet to consider that question seriously.
Mm-hmm. Okay.
Yeah. So then corollary of that's a representation. Okay, before this I go, so I want to say this. You notice this representation is really general representation. You notice I even have not yet to take expectation. So this expectation is taken for the Brownian motion, E naught, for the Brownian motion, which is artificially introduced. But for us, for the chaos expansion, this representation is in the quenched form, in the sense I have not yet to take expectation. So that means we can do some other things in the future. Now, the corollary of this representation, now I'm going to take expectation. So I'm going to make a, so that's the corollary. And that basically, you say that's a link to our moments. So remember, the moment representation is this part in our chaos expansion, where that's the time is unified to be one. But we cannot, like I said, we cannot directly deal with this. So we consider that exponentiation of the time, this is a multiple exponentiation time. So multiple exponential times. If we do this, then immediately we associate our moments to the Brownian motion, more precisely to the intersection local time of the Brownian motion. You can imagine later on when you do that, take the limits, that's the knowledge of intersection local time of Brownian motion or self-intersection local time of the Brownian motion will play a fundamental role in our computation. Okay, so let's see how this will be proved. You start here basically before you take expectation, and by the simple algebra you can represent your, the moments into the form like this, and keep in mind this thing can be written in terms of the Brownian motion related moments. That is used as the representation here. So then just by the simple algebra, and you can write that into the moment where inside is the sum of the terms created by P independent Brownian motions. Okay. Once you have this, then you just look at this moment. If you condition, so you are going to take the expectation, next page, you are going to take expectation to the Gaussian field. If you do that, and the conditioning on the Brownian motion, and the sum inside will be a normal random variable. That's what I said. That normal random variable have a zero mean, and the variance is given by this. Essentially, that's an intersection local time. So if you take the moments to the normal random variable, then this will give you, just use that the moment formula for the normal random variable. So that will give you this, that will complete our proof for the corollary. So how do we use the corollary? In this talk, we use the corollary to give the result like this. Okay, so before we move on, I wanted to say what the stage we are in our proof. Remember, I said the key part of complete our proof is asymptotical behavior of this part with the Tj be unified as one. Okay, we cannot directly do that, so we take that exponential time. So if this is done, you can say that the next step will be kind of taken Laplace inverse and to back to the time where back to the case where the time equal to 1. So that's kind of a Laplace inverse. So that's our plan. Now to prove this, and by our representation, all you need to do is just show that the following limits. Simply just replace this by its representation in terms of Brownian intersection local time. So you can say that for the proof of this part, the large deviation for Brownian intersection local time, that includes the mutual intersection local time and self-intersection local time together, that will play a fundamental role. But due to the the time limits, I will essentially skip this part, just quickly go over this. Well, I'm not going to, I will go some part of this. So if you wanted to do this, so you notice that inside this moment, the terms are not independent, right? although you have an independent Brownian motion, but those are term forms chains that link one to another. So the terms are not independent. So what you wanted to do is you wanted to do something to make that the sum inside this moment to be independent. That's what we do. So we do a simple algebra. So first of all, we try to write this, quadratical form in terms of L2 norm. So we do that Fourier transform. So once we did the Fourier transform, we did some simple algebra trick, and then we play with the Gaussian inequality. Okay, this is a play with the Gaussian inequality. So after this is done, now you say that you have a different quantity where that's the sum, where you have a sum in which that's the terms are independent because the Brownian motions are independent. Then what you can do is just, replace the original moment by this moment with the independent sum. Then just, do some kind of moment calculation. Here, I don't want to do that in details. I will quickly run.
结果我隔天早上起来，我手机完全没有充到电。
还有另外一种可能，电话没有这个 message。
Okay. So this is in earlier literature I'm going to use for those the calculation of those moments. Then after that, then you are going to change the problem to something easier to manage. So that's the kind of the procedure we went through, and that is to use that intersection local time large deviation. I'm not going to emphasize on that. So in this way, we get the upper bound. For the lower bound, also is not quite new. So I'm going to quickly go over this. So that's by basically you have a L2 norm. You just do this trick of the Cauchy-Schwarz and to make the linearization procedure. And after this and this, you can reduce this moment into the form of this, and then that's the arguments, the typical arguments we can use for the kind of by this spectral representation, and will leads us to something like this. Then we use some kind of the argument by spectral analysis to give us link the problem to the principal eigenvalues of certain linear operator. Okay. So that's how we get this part. Okay. Now, so the next step is to remember we are not interested about the moment with exponential time. We are interested about the moment with the fixed time, the time t equal to 1. Okay, so this state, that's what we are interested. So to go from here to there, that's a kind of an inverse Laplace transform. Okay, we first do that for the upper bound. So you start with this quantity, and by the previous discuss, we know exactly asymptotic behavior of this quantity. We just try to link that to that's the quantity without exponentiation. So here is what we do. First of all, we unify the time. We understand this all moments have a scaling, but that scaling only be there when your time is unified. Here, the time is not unified. You have a different time, T1 up to TP. So to unify the time, that's you replace that's a TJ by, that's the minimum of them. And here you use the monotonicity of the moment. So that's where we need that to assume that the dimension D is 1, 2, 3, because in those dimensions, that's the G is non-negative. Therefore, you have a kind of a non-negative integrand here. So that will be monotonical in time. Okay. So you can, by monotonicity, you can do this step. Then this moment, once you change the time to from T to 1, that is independent of T, so you can pull that out. So what's left? Here is what we use as scaling. So is this. Now let's say what is our situation. We know exactly what the behavior of this term, the term we start. And we want to know the behavior of this term, but you can imagine that this part can be easily handled. So in this way, we get something about that's this moment. So that's the next page. So we wanted to handle this part. And you remember that's the, so the fact that if you have a P independent exponential times, if you take a minimum of them, that's still exponential time with a parameter P. So in this way, you can change this P multiple integrals into single integral, one-dimensional integral. And this integral can be easily evaluated in terms of the gamma function. So when you deal with the gamma function, you use Stirling formula to write that into the power of some n factorial. And so bring that to this page. So you have this part in the form of power of factorial. So you can write this also in another form of n factorial, and you throw this to another part, and you get that upper bound that we want. Okay, so that's the proof of the upper bound. So if you want to prove the lower bound, the idea is you have to reverse that direction of the argument. So first we wanted to try to use that argument. Here, if we limited our T1 TP into basically very small areas, then you can say that all those T's can be essentially bounded by the smallest of them. And then that's the way we reverse our the estimate. So you are going to get some estimate like this, where you are allowed to play the game of the scaling. So the scaling is out. So again, you see this moment. So if you bring that to our argument, so now instead of consider that the time integrals in whole space, you just consider that this time integrals in the local domains. And all those arguments in opposite directions works. So you get the quantity we want. And this part, since delta it can be close to 1, so this thing will not make the contribution when you take that the large deviation. And this part here, you can throw to another side. Okay. So everything works except that one thing missing. That is this. So far, we don't know what's the behavior of this time integral. we know if you change this to the whole space, we know that's what's the behavior of. So, but we can make this thing up if we have this kind of quantities, this kind of relations. That means a kind of a concentration behavior. So when that's when n goes to infinity, that's basically this result shows that the most of the quantities of T1 and TP concentrate locally on this small domain. If this is true, then the problem solved because we know the behavior of this and use our previous argument that gives a lower bound. So now the question reduced to one problem, that is this concentration behavior. So let me just say something about that's how we get over with this concentration behavior. First, remember that we have used this quantity, and that's one of the major steps in this talk. You notice that we did not use, fooling about the generality of our representation, because in our representation, we allowed that the coefficients in front of T to be different. So if you work harder on this, you can get something similar only for the upper bound. I believe this is sharp. I believe the lower bound exists, will be the same as the upper bound. The reason I believe that is because when you take this lambda, all lambda equal to 1, and this part will equal to 0, that's go back to this result. But and this moment cannot prove the corresponding lower bound. But the point I try to make is we don't need the lower bound for this. So essentially, we use the upper bound to prove the lower bound. Right? If you know that you read some, that's the textbook about the large deviation, there's one place where when you prove the Gardner-Innes theorem, you first prove the Gardner-Innes theorem for the upper bound, which does not need many technical conditions. Then you use that upper bound to prove the lower bound. Here, we just partially inspired by that idea. So that is what we do. So to make the argument work, I'm going to construct the probability measure sequence like this. And use that our results for the numerator and for denominator. You can have this kind of upper bound result for this. So basically, asymptoticals for this exponential moment. Why we need this? Where this is lambda, so that's the game here. Why we need that? Because by that result, you can use the upper bound of Gardner-Innes theorem, what I mentioned just before, and to get the upper bound. I just want to make a remark. The argument for the upper bound of the Gardner-Innes result is essentially the Chebyshev inequality. So they don't need those technical conditions such as the smoothness, essential smoothness for the lambda function. So you get this. And where that's this lambda star is just a conjugate of the lambda. So since this lambda is specifically given, so in principle, you may be able, you may consider to get the closed form of this lambda star, that's the topological conjugate. This is an elementary problem, but it's a hard problem to get. So like I said, it's not easy and not necessary to get the closed form of lambda star. But all we need is just to get the concentration phenomena. So what we need to prove is okay, so the general phenomena is this lambda star as a rate function will be non-negative. But what non-trivial thing we are going to establish is this lambda star will keep positive except only one point. That point is all those t's equal to 4 minus alpha. So that's all we need. So in order to do that, just doing some kind of elementary trick and to get there. And so that's basically the trick. Shows that lambda star keep positive and the place where the t are not not equal to 4 minus alpha. So by those kind of regularity for the rate function, you can strengthen this condition as that this lambda star, when you take in frame to the areas outside the neighborhood of 4 minus alpha, this thing to be positive is keep positive. So if that is so, that by the upper bound of our large deviation, this thing will be keep strictly negative. And remember, what's the definition of mu n? That's what particularly tells us that this is the main constant. So that's the quantity of this is mainly concentrated on this small neighborhood. That's the concentration phenomena we try to establish to complete the proof of our theorem. I think that is the proof. And here I just to end my talk, I wanted to mention some relevant literature. And the first literature is basically is the intermittency problems in the system of the Skorohod. So what we are talking about is a different system, but you see that we get the more or less the same result, but with a different kind of ideology. The second was the recent result of Balan, which is talking about that's on the same system, but for the problem of solvability. This part, at least here, is mainly about that's this kind of asymptotical or large deviation for intersection or self-intersection local times we use in our to establish this result. Well, here is another paper where we talk about the case where that's the Gaussian noise may depend on the time, but in this paper we were talking about the issue, the problem of existence and uniqueness. I try very hard to establish the intermittency for the time-dependent noise case, but still I say that I feel I'm not even close to solve that problem. And finally, then this result is kind of a classical result. That's essentially they consider that the deterministic wave equation, and they establish something they call Feynman-Katz type formula. Indeed, that's just an expansion based on which we have our result. So that's a relevant reference I can think of at this time. Thank you, and I apologize. I don't know what's happening. Maybe that's yesterday was Halloween, something happened. So I missed some pages. I could not find it, and I think I'm a very careful person. I checked even yesterday that all the things, try to make sure nothing wrong. But since that's Halloween, things happening, I apologize.
Okay, thank you very much. It was a pleasure to see your talk because it reminds me like in fighting when you don't use sword but use rapier. It is much more heavy but much more efficient. So thank you for interesting talk. Just before I ask for the comments, let me do the comment that in my book, Stochastic Analysis and Random Maps in Hilbert Space, there is a section devoted to some kind of analog of Fourier transform related to Gaussian functionals. And this Fourier transform moves Skorohod integral into Stratonovich and vice versa. So maybe it can be interesting just have a look on this section and try to connect both solutions.
Okay, thanks for mentioning that. Actually, during the time I prepared this, we were thinking about the mathematical problem for this case. The first thought is to see if there are any connections between those two systems, because in a Skorohod case, there are some nice things to use. For example, you have orthogonality, and you have that's a hypercontractivity. My question and immediate thought is if we can make the comparison between the moment, Stratonovich moment, and Skorohod moment, that will be wonderful. But I just could not find that's anywhere mention this. Now I hope, Andrew, you are going to send us a reference.
Exactly. I will send you the book. And
yeah, that will be nice. So, for example, that's in a Skorohod case, very powerful. That's the tools is hyperconductivity. Yes. But we don't have this here. It would be wonderful if you found the relation between Stratonovich moments and the Skorohod moment. That would be very nice. Okay, thank you.
Okay, thank you. And maybe somebody have questions or comments, please.
Sorry, I have a technical question. Can you handle exponential moments? So,
exponential moment of
the velocity field.
Of solution or?
Yes.
No, actually, let me just tell you why. Okay, so this is our major step. Remember, this thing is the general term in our expansion, right? Okay, and then you look at this power of factorial, which is greater than 1. So when you take the summation, this thing, that's a yes. So the moment is this, but when you use a Tyler expansion to put those things there, this will guarantee that the things will blow up. So we have a super exponential increasing rates. When you take that the Tyler expansion to get the moment generated function, that will blow up.
Okay, thank you.
Okay. Some other questions, please.
Or maybe I should, can I just say something more to answer your question? Maybe that's the better way to do that by look at this result. Yes. You say that, okay, so the P, okay, now this is one of the results we did not, okay, the second result, where we did not prove, but that's also one of the results. So you say that if you take that P to be integers, and you say that if you take that to be integers, then you take that the so your question is to ask exponential moment of u, and I think that by Taylor expansion, this indicates that will blow up. Yeah.
That's right. That's right. Yes, it's just my point is that if you take something like KPZ, then
Sorry?
if you take something like KPZ, the polynomial moments grow very fast. Still, but still the exponential moments exist. You just need to compute.
Okay, let's see.
different way. The moment problem is ill-defined.
I will, okay, so you are basically, your comment is referred to this quantity, right?
Yes.
Let's see, that's what you will get. I'm not sure, so this will tell you yes or no, that's immediately, but since now I did not think of this problem carefully, perhaps from here you will get the answer by yourself.
Sure. Yes. Thank you very much. Yes.
Okay.
And can I ask a last technical question, perhaps? So, if you are interested in the high order moments of the solution, so this is naturally a large deviations regime, right? So you are
Yes.
sampling the tails of the U distribution. Is there any way to get these results from a large deviations principle for the original SPDE?
From original SPDE, okay, here is the things is, first of all, I want to start to talk about this for the parabolical equation. Okay, this is hyperbolical equation. Where the parabolical equation is where that's your time just take a one derivative, not two derivatives. So in that case, sure, that's the answer is yes, because you can immediately write your solution in terms of exponential moments of the some function of Brownian motions. Then whenever you say that's the exponential moment, of course, then that's basically is a subject you almost can directly apply the large deviation theorem. In this case, in the wave equation or hyperbolical case, like I said, there's no such moment representations. Now, before this talk and before our results, all you have is that series expansion. You cannot write the closed form into one term. Even in that series expansion, there was no position for the Brownian motion. So in their expansion by those Dalang and other two authors, they introduce some process which is not even Markovian. So all those things cannot apply there. So of course, this become that's why I start to think about those kind of models, the models where the large deviation cannot directly apply. For example, you have expansion, regardless you talk about the Skorohod system or Stratonovich system, you have an infinite series expansion. What this expansion will provide the base for your argument. That's what I'm concerned. So yes, so that's the reason I'm interested about this model is because it's not a direct large deviation problem. Okay.
Okay, thank you.
Could
Thank you
please,
again.
may I ask
Some
a
other question?
Yes. Could you please explain one more time your trick when you replace T1, Tn via by minimum? You used monotonicity
Oh, yes,
or positivity.
Okay. So I will make this remark. In my personal experience, I found out that let me just go that page, then I make a remark. Okay, here is the stage we're talking about. You have an exponential time result, and you wanted to do inverse Laplace transform. The general remark I want to make is, I found that the exponentiation of the time is a very useful tool to simplify many of those problems. But sometimes I wonder why it's not so popular among those our researchers. The problem, I guess, one of the problem is, then unlike the Fourier transform, that's a Fourier transform, that's the transform and the inverse transform take more or less the same forms. So it's very relatively easier to take inverse. But Laplace transform, although in principle that's a one-to-one map, but the inverse looks very differently and sometimes involves some of those complicated quantities, not very easy to apply, especially applying to some asymptotical problems like large deviations. So that's how I try to work on that inverse. Now here, we found out. So here is, first of all, you want to unify the time. Of course, when you unify the time, when you start to work on this, there are two ways to unify the time. Either you take that's the minimum of them, or you take the maximum of them, right? But which one will represent that's the truth? Of course, now we know that's the minimum of them. Actually, the times you need a little bit of, the thought, because one of the thoughts I feel good about the minimum of the time is because minimum of the exponential time still exponential, but the maximum of exponential is not exponential anymore. You don't feel good about the maximum, the first one. But once you use that's the minimum of the time, of course, that will give you one story up lower bound. If you believe that's the lower bound, that's you must believe there is a concentration, okay, of this time. Otherwise, you are not going to get there. Then the next question is concentration to what? So by here, that's when you say this kind of things, you will say that maybe that's a concentration to that's a 4 minus alpha. Why? Because when you say this kind of quantities and you want to associate with some basic distributions or basic laws in probability, in my mind, I'm going to think about the gamma distribution, right? So the keep in mind the gamma distribution have additivity. That means if the P is fixed, this thing can be written as a sum, independent sum of those small gammas. So then that will tell you that you may have, so this thing is, if you wanted to know what's the behavior of this integral, well, immediately I'm going to think about the law of large numbers, right? So law of large numbers is a kind of a law give you the concentration. This thing, just think carefully. You may think, okay, so that will, before you know everything, that will tell you perhaps that concentration will on this 4 minus alpha. because 4 minus alpha is the index of those small gamma functions at, from 1 to up to n. So once you notice that they have a, the concentration may apply, then that's why, that's the no problem if I replace this, whole, space by this, I'm not going to last too much and still get the kind of same quantity before. So I think that's how I get there. So.
Thank you.
Okay, thank you. Some other questions, please? If no, then thank you again very much, and I hope to see you personally, not in Zoom, sometime.
Right,
Yeah.
that's also my hope. So let's see all those bad dreams will end soon. Okay, thank you all. So.
Okay, Georgi, do you know who will be the next speaker?
Yes, it will be Ekaterina Glinina.
Okay, thank you. So for today we finish our work. Thanks everybody and bye.
Bye bye.
Goodbye.
Bye bye. Take care.
Bye, thanks.